Hello, dear friends. A great welcome to the series on Idea Statica member. Myself, Jarajan P. It's, in fact, after a very long time, I'm taking you to a new tutorial. I'm really sorry for the same. This is tutorial number 36. Here I will demonstrate how to verify a continuous beam laterally supported only at the supports using Idea Statica member with respect to Eurocode EN 199311. Now, before taking you to the Idea Statica, let me you to the problem statement. As you can see, the beam that we will design in this tutorial is a continuous beam as shown here. It essentially has two spans, each of say 5 meters. It carries a uniformly distributed load, that is a W intensity, and the material of the beam is S355 steel, and the section considered is IP300. And in fact, we have considered two limit states, and one is the ultimate limit state that corresponds to the design level, for which W is evaluated as 10 kN per meter, and for the serviceability limit state, the calculated W is 3 kN per meter. Now, for IP300, the plastic moment of resistance that is computed as per the Eurocode 3 works out to be 223 kN per meter. But as you can see from the Idea Statica tutorial, we'll find that we'll not be able to make use of the full resistance of the material because of the lateral torsional buckling involved, and the reduction factor that is evaluated from the Idea Statica works out to be 0.46, and accordingly the beam moment of resistance considering the LTB will be much lesser than 223 and is calculated as 102 kN meter. Therefore, LTB governs the beam in this specific case. So let me take you now to the Idea Statica tutorial, which is essentially Idea Statica member. Okay, fine. So this is Idea Statica member screen. So we'll start with the project name. I'll just call it as a continuous, and I'll just select a project folder. So browse it. So I'll just pick some folder. I'll select the folder. Now, as we've already discussed, the project type here, which will be the steel, because we are analyzing a steel continuous beam, and the design code that is selected will be the Eurocode, and the steel grade in this tutorial will be selected as S355. And as you can see that here there are different kind of geometries pertaining to the beams, columns, and the bended beam. And here we'll select the beam, and as we have already discussed, it is a continuous beam with two spans each of 5 meters. So we'll just select 5 meters and 5 meters. And the cross section in this case, what we'll do is that we select it to be IP300. So we'll select the IP profile, that is the IP300. So as you can see that this is my IP300. Okay, that's fine. So we can select as okay. So we'll ask the Idea Statica to create a project for you. So this project will obviously will show you all the members that are generated as shown here. So now as you can see that here, if you see here the entire beam, let me just zoom it. Here you will find that there is a support to the column. That this is the beam that we have generated. It is connected at the two ends of a column, right? And at the end, in between, you will find that there is something like a rectangular box. Here we need to create a support also. Okay, so now let us just go for the model development. We'll just go on editing all these default parameters that is generated by Idea Statica. So let us go step by step. AM1 as we have generated an IP300, and EX, EY, etc. will set as 0 and alpha will be 0. And as you can see that it has generated this member, that is a AM1. AM1 is the analyzed member as a single member of 10 meters, and we know that it has to consist of two spans, right? Now let us go for the definition of the related members. Now here, for example, RM1, I don't require RM1. Also, let me just know what it is RM1. This is a member which I don't want to have it in the analysis. So what I will do is that I will simply delete it. Okay, so RM1 is deleted. Now as you can see that RM2 is basically a column okay, to which my continuous beam is connected. Now let me just go on editing the parameters of the RM2. It's a column, so what I would do is that I would like to have it as well a little bit larger one cross sections. I would go for an HEA profile. So let me just call it an HEA, and I will go for example HA 240. Okay, so the material will be as the same. Okay, so fine. So I have generated a new section for my column, and you can see that here this is the member. Remember that these are the two ends of this column member. This is one end, this is another end. Okay, so now we'll go for example, Idea Static as generated it with as a total of, say, for example, 4 meters each piece. What I will do is that I will try to reduce it a little bit smaller. So what I will instead of 1 instead of -4, I would make it as a -1, so that each piece will be having only, say, 1 meter length. And here I'll just change it to as, say, 1 meters. 1 meters. So here you will find that yes, it is reduced because this is just provided not for analysis of the column. It is meant for analysis of this continuous beam. So it is a material, what the length is for me. So I kept it as a smaller one. So and then the boundary conditions, that is the supports for this member. That is, you can see that there are two supports. Yes, this is one support and another support. We need to provide the boundary conditions. For the time being, I created a support so that XYZ displacements are restrained. Also, the rotation about the x-axis is also restrained. And remember that all these conditions are being fed into the system under the local coordinate system. Okay, so this is all regarding my RM2. That is the column on the left side. Now, let me take you to the other members. Now, coming to the RM3. RM3, again, I would like to have it on let me just zoom it. Yes, this member, as you know, it is not required for us, so better I will go straight away for deleting this member. And now we have the RM4. Now this RM4 is again a column. We would like to have the same prescriptions that we kept for the member RM2. So as usual, what we'll do is that we'll simply change it to an HA240 member. So just click it, and we can change it to an HEA profile. So this HEA 240, we can have it. Okay, it's okay, fine. And obviously I also want to change the length of this column. So instead of this -4, what I will do is that I will simply type this as a -1, and here I will keep it as just 1. So you can see, you can just edit it 1. So you will find that a column of total length 2 meters is only generated here, and the boundary conditions are kept the same as RM2 on the other end. Okay, and now we have to generate an intermediate support. All right, and also in Idea Statica, what is very important is you need to develop some restraints or some members where you want to restrain the beam. Now in this case, as I have already explained in the first 2 pages, this is the analysis of a continuous beam with 2 spans, and I assume that this beam, it is only restrained at the support location. That means in the 2 span location, it is not at all restrained. Okay, that means the spans are not laterally supported, and the support is being provided only at the intermediate location. Okay, so here what we need to do is that we need to select one intermediate support, which is essentially a vertical column, and also another beam has to be generated, so that will provide a restraint, a perfect restraint to the continuous beam at the intermediate support. So what we have to do is, first of all, just let me see. Okay, first of all, you need to select the analyzed member AM1. Okay, so and in the analyzed member, what you need to do is that we have to generate an intermediate point. So this is an intermediate point. So it will ask you where you want to create this intermediate point. Obviously, we know that the total span of this beam is say 10 meters, and you want to have an intermediate joint at say 5 meters. So instead of 0.5, what you do is that you straight away go for say 5, right? 5. And what you can do is that we want to have an related add related members ended. So for example, suppose I want to add a column which is not continuous, it ends just below the beam. So what I will do is that I will add related member. So there are 2 provisions. One, either you can add an ended member or a continuous member. I want to add an ended member which stops at the beam location. So, and I want to add it in the Z direction. So you can see that at Z direction. Okay, so look here. Now we have added successfully a column at the intermediate location, and this is a support. In fact, this is a supporting member for the continuous beam. So you will find that a member is automatically created, that is RM6. Okay, so what you need to do is that you can quickly change the properties of this. Okay, what I will do is that as it's an intermediate location, I would like to just go with an HE section again, and in the HEA also I would prefer for easiness a little bit larger section, HEA 300. Okay, so and it is as 355 the same. Okay, and here as you can see that here again we will keep the same 1 meter length only, and the boundary conditions are kept the same. Okay, now so we have modeled the intermediate support. Now we want to create a beam in the y direction, and this beam which we are going to create, it will provide a restraint, and this beam is going to critically affect the analysis of this continuous beam against the lateral torsion buckling, or it will critically influence the linear buckling analysis that is being carried out. Okay, fine. So now we need to generate a member that provides a restraint, or it will introduce the restraint to the buckling at the intermediate support. So what we need to do is that, as you can see that, okay, we need to generate a member in the y direction. Okay, this member. So look here. So we have generated, we have RM2 which is a column, RM4 is another column, and RM6 is our intermediate support. Now what you need to do is you need to generate another member here. So let us do through the connection. So look here. So when we have developed our model, Idea Statica has automatically created the connection also. And these connections need to be obviously edited from your end as well. So you can see that connection 1 stands for this location, connection 2 stands for the intermediate location, and connection 3 it stands for the end location. So what we do is that go to connection 2, that is the intermediate one. Here you will find that in the edit connection facility we have the facility to add the members as well. So we want to add a member in the y direction. So what you do is that you click here y. Okay, so you'll find that yes, already another member is added, and this member is specifically added in order that the member is restrained against the lateral dorsal buckling at the intermediate support. So you can just edit the member. So this we have kept it as IP 300. Okay, and all these things will remain the same. That is, remember here that it is added in the y direction, and it is a basically is a ended member. It is provided only on one end, and the boundary conditions are kept the same. So now we have created all the members, right? And that is a 3 column members, one indicating the intermediate support, and the other provided for the lateral restraint. Now it is a time that we start going and editing the loads. So we'll straight away go to LE1, right? In LE1, what you can do is that you can define the load. So I will keep it as ULS, that is my ultimate limit state, that will be used specifically for the design purpose. So I need to apply the load on this entire member, that is AM1, and it will start accordingly from 0 to 10. Okay, and it should be applied in the z direction, that is -1. And remember here one very important thing, though Idea Statica has written as a line load, okay, we want to apply it as a pressure load. Okay, so what we'll do is that we assume that this loading is acting over a width of 100 mm. Width of 100 mm means, that means it is up over this 100 mm. That means if the flange width is, say for example, say 200 over 100 mm, this load will be acting. Okay, so that means, so this will keep it as, say for example, say -100. -100 means what will be the load per unit length of the beam? It will be -100 into the width over which the load axis we are considered as 100 mm. So it does mean that this 100 kilonewton that is applied, it is equivalent to 100 into 0.1, that is equal to 10 kilonewton meter. Okay, fine. So because we are talking about a pressure load, so we have applied the uniformly distributed load, that is equivalent to 10 kilonewton per meter, corresponding to the ULS. Now what you can do is that you can just go on adding one more load case. So what we can do is we can just add another load case LE2, and obviously in the LE2, so we can just add plus and add it, and this LE2 will corresponds to my what we call as the service load. service load characteristic. So we will use the same member, and but this load will be a little bit reduced. So you can say Z as, so it is minus 30, which represents minus 13.1, that is minus minus 3. So and this will generate as, and remember here there's a one known as location. In Idea Statica, it is possible for you to apply the load either on the top flange or on the bottom flange or left edge, right edge, or the member axis. I want to apply this load on the top flange, and accordingly it will I can provide my the width over which I want to apply it, that is 100 mm. So this means that I have applied a load of 3 kN per meter in the downward direction for SLS characteristics. So we have finally generated the loads also. Now it's time we proceed for editing all the connections given over here. To reduce the time, I have generated all the connections, and I don't want to provide you all the details how the connections have been added. And if you have practiced Idea Statica connection, you must be able to understand it. So let me just show you what are the 3 connections that I have developed. And so I will select connection 1. I'll just show you. So I will just edit connection so that it will show you what are the connection details. And if I include all these details of the connection also, then the video may go up to say 45 minutes. I don't want that. So we are now in Idea Static connection. Yes, look here. So here I have already developed the connection between the column and the beam, and as you can see that, okay, so this is the connection. It's an end plate connection, and I have used a total of 6 boards arranged in 2 rows. And you can see all the details over here. It's basically an end plate connection. All the details are being provided here. So that's all regarding the first connection. And the second connection, it is almost, you can say that it's the same as the connection 1, right? So let me just show you what it is. So as you can see that, yes, this is a connection that I have provided or developed at the intermediate location. And so look here. So as far as this beam is concerned, connected beam is concerned, okay. So here you will find that I should have kept the top of this member corresponding to the top of this beam also. Okay, that we can also do later, right? So that look here. So this is an end plate connection. And regarding this column, that is my intermediate support, you can see that the connection is being again done using the end plate. So in general, I want to tell you that for all this continuous beam joints, I have used an end plate bolt connection. And one thing here I want to mention, this Idea Statica member, it will never design any connection, right? It will not check any of these connections. The purpose is that, and one another important point is Idea Statica neither asks you what are the boundary conditions, that is whether it's a pin tent or it is for the continuous beam, whether it's a fixed tent and all, and it involves or it calculates support conditions itself based on the rigidity of the connection. Okay, fine. So this is my RM, this is my connection 2. Now connection 3, obviously the balance connection is this one, and you can get a snapshot of the connection here also. Connection 3, if you see, you will find that it is this connection, so you can just edit it. It's almost like you have the connection 1, and you'll find that it is also the same end plate connection. Okay, so fine. So this means that we have completed the model and we are in a process of starting the analysis. Now look here, as I already told you, Idea Statica member has got 3 modules. One is the material nonlinear analysis, and the material nonlinear analysis will tell you what exactly is the resistance of the member or the moment of resistance of the member without considering the LTB. Okay, without considering the LTB. If you want to include the LTB, you have to go to a second analysis that is known as the linear buckling analysis. So first what we do is that we straight away go for the MNA, that's the material nonlinear analysis. So what we can do is that we can just press this calculate so that it provides you, okay, what is the moment of resistance of the section, okay, if it would have been fully restrained, right? Now if you want to understand what will be the possible expected reduction in the moment of resistance due to the buckling, if it is present, you have to go to the second stage of the analysis, which is known as the linear buckling analysis, which will be covered after this MNA. So let us just wait for a small time, maybe that it takes say 30 seconds. So let us just wait so that it provides you. And I would request you to make a hands-on experience with all these things. And in my experience, this Idea Statica member, it will be a very good, powerful tool, especially when you want to analyze deep girders, you want to analyze a gantry girder, or you want to analyze an equipment structure and all. So this is a very powerful utility because it provides you all the direct effect of the buckling, and it also will tell you how you can directly or indirectly control the so-called buckling phenomena. So let us wait for, so maybe that it will take another 10 seconds time. So this MNA will provide you, okay, the bending moment diagram, the shear force diagram. It provides you the strain distribution, stress distribution, right? And if you remember, we have already calculated the plastic moment of resistance is something around say 220 kilonewton meter, right? So let us first see, okay, fine. So the MNA, that's the material nonlinear analysis, is calculated. It has shown you, means it is possible to do the analysis with 100% of the applied load, and MNA of the plates. So this provides you what is the strain, what is the strain level in the plates. We find that is 1.1 percentage, saxophone is less than say 5 percentage. So now let us go for the results. So let me just go for the check. So here, first of all, I would like to do it not as a deformed one. Deformed one we'll see later. Okay, fantastic. Now let's go for the strain. We first of all we want to identify where are the critical sounds as far as this continuous beam is concerned. Obviously, we know that the critical sound it should be at the intermediate support only, right? So let us see it from the strain distribution. So as already indicated here, it is 1.1 percentage. Here it is 1.2. Now I just want to tell you one a relevant thing, that is we are interested only in the strain levels of analyzed member AM1. So please cross check whether this MNA of the plates it corresponds to the analyzed member. If it corresponds to the column or the supports, okay, don't take it as a governing criteria. So let us go here. So you can say that MNA results are here given. Yes, AM1 is analyzed member. We find that this a critical strain corresponds to the analyzed member only. So it is not a problem for us. And for all the support members, we don't have any problem. Because I have seen in some cases people confuse, oh my god, the strain level is 10 percentage. Maybe that this 10 percentage could be the strain level in some supports. But don't worry about that. Okay, so we need to focus only on the analyzed member. So we find that the strain levels, so let's just zoom it where it is. Yes, look here. As expected, we find that there is a stress concentration at the intermediate support. You find that you see at the top as well as the bottom, right? Flanges, we have got the so-called maximum strain levels. So that is very important because any result analysis, okay, it should be such that you will be able to give an interpretation, and at the same time you need to have a feeling that yes, the things are happening in the way you would have imagined. Now let me quickly take you to the minimum diagram. So what I will do is that I will straight away go for the internal forces. So look here. So this is what is being expected. So you can see that this is the minimum diagram. You find that at the midspan we have got approximately 178 kilonewton meter, and at the support we find that it's 213. So 213 means we have calculated the plastic moment of resistance somewhere around 220. So obviously the strain level should be somewhere in the region of 0 to 5 percentage. So that is 1.1 percentage. Okay, so our analysis has proceeded in the right direction. So look here. So this is the minimum diagram of the analyzed beam. Now suppose you are interested in, for example, the shear force. What you can do is that simply go for the VZ. Okay, it provides you the shear force diagram. Yeah, look here. This is the shear force diagram that we have provided. We are not interested in the shear forces or the bending moments in the connector supports or the columns. We have to focus only on the so-called analyzed member. So having done that, so let us also quickly see what will be the stress distribution. And remember that all these checks we are doing for the LE1 right now, which corresponds to the ULS. Let us quickly see what is the stress distribution. So in the stress distribution, you will be able to see which are the what we call as the critical parts. So look here. So let me just go for the stress distribution. So yes, it will take some time so that we were in the Schaeffer's diagram. Look here. Now let me just keep it as the internal forces I don't want. So look here. So the stress distribution. So we are in the stress pattern. It should provide you. Let me just remove this deformed shape. Takes some time because refreshing it takes some time. So you need to be patient. So look here. This is what we have expected. Our stresses, our stresses are not that much critical. Okay, at the you'll find that look here. This section is almost it's at the 355 level, right? Midspan section, it's almost critical. Okay, the support section, it's almost critical. So and the stress distribution, and you'll find that at the midspan, the stress concentration is almost because it's a lesser moment. It is rather concentrated near the flanges. It does not drop down to the web portion, and here you'll find that the entire section is almost in the verge of plasticization. So this is regarding what we call as the stress distribution. Now let us quickly check what we call as the the deformation, right? What will be the whether the deformations are within the acceptable limits. So remember, deformations are to be checked under the LE2, that is which represents the serviceability. So let us quickly see what will be the deflection, whether the deflections are within the permissible limits. So look here. So remember, this has to be my LE2. Okay, LE2, and rather we are looking for the UZ. Okay, that is basically the vertical deflection. So you'll find that here under LE2 the deflection is a maximum. It is at a 5 mm, 5.6 mm, and that is essentially as expected somewhere near the mid spans. Okay, so this is all related to what we call as the material nonlinear analysis. So we find that yes, the material has enough strength to take the belly moment. Now the thing is that all the entire span is left, unsupported. So there's a possibility, a very possibility that there's a torsion buckling taking place. So what is important is that the next stage we have to proceed for the linear buckling analysis. So what you do is that you will select the LBA, that is nothing but the linear buckling analysis, and again calculate. So this linear buckling analysis will provide you all the critical buckling modes, the effect of the what we call as the buckling on the beam strength. It also provides you what we call as the buckling shapes. Okay, and so that you can easily identify what are the critical buckling modes over which the beam strength is decided. Okay, fine. So my buckling analysis is over. Now look here. Here in the buckling analysis, it has provided you. So let me just take you to the. Okay. So look here. In the linear buckling analysis, there is a factor of 0.46. Look here, LE1. LE1 is a 0.46. What does it mean? This indicates that the material do not have a strength of, though the material has got a plastic moment of resistance of MP, due to the lateral torsion buckling, it has in fact has got only a resistance of 0.46 into MP. That means lateral torsion buckling will reduce the strength by almost up to say almost by 50 percentage. Now let us quickly go for the motifs. So to get the motifs, what we can do is that let's say look it directly from the top. So let me just zoom it here. Look here, it's a very beautiful shape. You find that it is something like a so one sine curve. Okay, so you can just have a look here. Yes, so you'll find that yes, it is a UI. Let me just say that. Let me press also the user here. So when it is a UI, it will provide you what are the total deformations in the buckling. So look here. So you'll find that this portion, it is the out of plane buckling deflection is maximum, and here also the same. So this is a basic what we call as the fundamental mode of the buckling here. So from this we can very easily conclude one thing. If you want to improve the moment of resistance of this beam, the best way is that you generate a beam here, or you generate a restraint at the midspan that will obviously shoot up what we call as the moment of resistance. So this is, for example, this is your first mode that will control, which is very critical, and wherein the reduction factor is a 0.46. That means the actual capacity will be only 0.46 into MP. Okay. Now, for example, if you're interested in the mode 2, you can select the mode 2 just to have a feeling how the mode shapes are looking like. So you'll find that it is an altogether different mode. So this is all about the buckling analysis. And so here, what is very important is that we need, if the support conditions are the same, it does mean that we have to revise the IP300 to some other higher size, IP450, or another possibility is that keep IP300 and then introduce an additional beam at the midspan. And this exercise wherein we will introduce an additional restraint at the load application, that will be covered in the next tutorial. And in this tutorial, please remember that we have added a restraint only at the support location. Okay, so for all this case, we find that normally for the IP sections, it is a LTB that governs the design, or the what we call as the design resistance of the section. And it is important that we provide a proper lateral supporting to the compression flange of the beam in order to improve the moment of resistance, or in order to minimize the buckling effects. Okay, fine. So that's all for the day. So please wait for the second tutorial, likely to be published in the next week. So thanks a lot.